Good afternoon, everyone. Today we are back with our EV webinar sessions, and today we have one special guest with us, Ankit Sharma. He has recently completed his MS in Masters in Electrical and Electronics Engineering from Coventry University, UK. He has especially worked on this topic converters. So today I welcome him to share his experiences and work profiles in this field. Over to
Well,
you.
thank you, Arun, and thank you, Abhishek, for inviting me for this conversation. And I really feel honored. And initially, I'll tell you one thing because I have done my internship with Autobot, so I met Abhishek over there. So I feel really glad that I'm speaking on today's topic. So before that, I would like to share some of my experience, and it would be really great if you could extract some information for you, which could be really helpful for you in the future. So, starting with the experience section, I got a campus placement in Merchant Navy for the post of electrical officer. So, initially, it was not like what I was assuming in my mind. I was thinking like I'll roam certain countries, I'll go here and there, I'll just meet with new people. But when you land up over there, things get really different. I mean, it is a job in which you need to be prepared every time. Like it's not like a 9 to 5 job, and it's not like a job which you feel like you will go at 9 and you'll come at 5. It's not 9 to 5, but after that, if there is something happens on the ship, you need to mm, be present over there, because as an electrical officer, there is only one person who takes care of all the ship from front to end and from top to bottom. Like there will be certain equipment such as main engines, generators, boilers, and each of the machinery will be having sensors, electrical panels, and a lot of wiring systems. And if I tell you frankly, to find a small fault on that big complex system is really tough, because when you do the troubleshooting, so you need to refer a circuit diagram in which can consist of 300 pages. So it becomes really difficult at that time to just find a simple thing from that complexity. And apart from that, there used to be different drills every Saturday and Sunday in which we used to test different alarms, like there were smoke alarms, fire alarms, in which we were told how to deal with different scenarios once we land up in case of an emergency happens on the ship. And normally we used to free ourselves after 5 p.m. during evening, but if something happened, then you should be present over there. But now, if I talk about the ships which are coming for the future, there are a lot of companies such as Rolls-Royce who are making the ship completely unmanned, which means that there will be a single remote station from you can control the complete ships. So automation, robotics, artificial intelligence, machine learning, as well as electric vehicle concepts is coming onto ships also. And you will see that these are not far behind when the ship would be moving without any person. Like it in today's technology also, maps are used to just provide a way to the ships, but a person is designated to do that work. Now days are not far ahead when you will see that it is all being done from a person who's sitting at a remote station, or who might be sitting at a normal company and is operating the complete ship without any person. So things are really getting advanced, because whenever I used to go on the new ship, I used to find different automation every time. So it was not like that I know completely because I've done two ships. So it was not like that. When I used to come on the other one, there was something new which I needed to learn. After that, I was really fortunate that I got a chance to do my master's in electricals and electronics. But a lot of people ask me that why you left merchant navy job. It's quite a handsome job with a good package. But the thing is, if you want to reach somewhere, you need to leave something, and that what was my goal. Because I was not very keen of on earning issues. Like I need this much package. My motive was always to learn about new technologies, and this electric vehicle gained my interest when I was doing my dissertation during masters. So I did my masters from Coventry University, UK, and over there I did my research internship under one project which was to calculate the silicon carbide traction inverter losses. So basically, in this, I was working on a PhD project, which was incomplete. So my supervisor asked that if we could do some calculation in defining what are the switching losses associated with silicon carbide inverter, that will be great. And due to that, I was also able to write a paper on that, which was about to be presented in a conference in Iran. And after that, I did my dissertation in electric vehicle designing an inverter prototype, which we normally see as one of the basic constituent in our electric vehicle powertrain. So in that thing, I just got to know the difference of the study purpose and practicality in terms of Indian and foreign culture. I'm not saying that Indian universities are not too good, but there are certain things which they need to seek and learn from foreign countries. Like foreign universities spend a lot of money on their research and development labs. If I talk about mine, there is a proper airplane jet which is there to teach aerospace and aviation students how the parts are working. Because when you deal with the practicality, 80% of the things struck in your mind. It's simple like that. If you're watching a movie, it'll be there in your mind for a lot as compared if you're cramming the things. Same goes with the practical things. And if I talk about the study kind of a thing, it's not like in India we just refer to a lot of books, but it's really great. I came to know that a lot of universities are making this electric vehicle car in the universities. Now you can see that it's a bit of changing scenario which is happening in Indian universities now also. Lot of universities are taking more attention to this field, and a lot of universities are making more investment in research and development. And I hope so that this culture study generation gap between Indian and foreign universities will decrease. IITs, NITs, and it should not be like that. That only IITs and NITs, these are universities, high level universities, which are imparting higher education and students and are giving those knowledge to the further the companies. But this kind of culture should be available in every university of India. So there should not be any distinction among the universities, which should be learned from foreign land. Because if you see there, every university is uniform in terms of teaching. If I talk about teaching, research and development, labs, and study. So that thing we can learn from those universities. And again, I'll come to my master's dissertation. So it was basically to design an inverter prototype, three-phase inverter, by using silicon carbide MOSFET switches. So earlier our plan was to use gallium nitride, but gallium nitride devices are a bit of expensive and were not available at that time in the lab, so we decided to do with silicon carbide. But what I did initially, I was keen to find the difference if we use silicon carbide or IGBTs of 1200 volt DC. So the component on which I was working, silicon carbide, was having a rating of 1200 volt DC. So initially I wanted to extract the differences of the different semiconductor devices. Like I took one silicon IGBT and silicon carbide MOSFET. So for testing them, there was a machine for testing semiconductor devices, which normally you will see Texas Instruments use for testing these switches. And on the basis of that, they prepared those data sheets. So there was one PhD guy along with me who really helped me for that work. So I came to know there are a lot of differences in terms of efficiency, if I talk about in terms of transient response, switching time, conduction time, and operating range, like voltage, temperature. So on the basis of that, I decided to use silicon carbide MOSFET for my device, and later on, for the programming part, I use one gate drivers. But as you know, to trigger the MOSFETs, there's a gate terminal, and for that gate terminal, you need a 5 voltage gate driver circuit. But you need to make sure that there should be a complementary switching of pulse width modulation among those gates, among those PWM switches, to in order to avoid short circuiting of the circuit. So for that, you need to program your complete circuit, for which I used an Arduino. And after that, I was able to present my results to supervisor. There was some mismatch, and there's a tool in Matlab Simulink which I think you guys must all be aware of, which is a tool through which you can measure the total harmonic distortion which is available in your circuit in terms of voltage and noise, voltage and current signals in terms of noise. So using the Matlab, I was able to identify that. But the most important part of my design was that I was using such topology, which was a cascaded dual topology to design my inverter, which was eliminating the converter part. Okay, I'll tell you. If you just take a complete example of EV powertrain, there are four main components starting from the battery, converter, inverter, and your motor. So the design on which I was working on, it was eliminating the converter part, which comes between battery and inverter. So how does that work? Because I was using a dual topology, so what it was doing, it was simultaneously converting your DC to AC, and also it was amplifying that voltage which converter used to do, like your converter boost up the voltage. That was also being satisfied by that inverter. So at the same time, it was performing both the operations. So that was the different part of my design. But later I came to know that converter is also essential, because if you need to supply for your external components like LEDs or maybe motor controller and your microcontroller, for that you need a converter. Then I presented my design during the project and during the presentation. So at that time there was some mismatch. There were some flaws which were present in my design, like the efficiency was not that good, but it was 60%, but still a 40% harmonic was present in my design. Like I was not having complete time because my visa was going to expire. That's why I was not able to do a lot of work on my project. But literally, I'll tell you, in these years, I have learned a lot. Because, and I'll tell you guys also one thing, that you should never take this money parameter in your mind. Money is important, I know, because you need to do everything and money is required for that. But if you stuck more on the money, your work will be a formality for you. And like electric vehicles which are coming in today's market, it's a booming technology, and I know it's a 3 to 4 years of gap of electric vehicles apart from the other countries, but still there are a lot of startups which are coming in the country like Aether Energy, which is decreasing this gap. And lastly, I have done my research internship with Abhishek, as I mentioned, with Autobot India, and I learned a lot in that. Also, we worked under motor controller, so we were three in a team, and I met Abhishek in that team for the first time, and I was really amazed by his knowledge on electronics and communication. So initially, I was guessing this guy might be from electronics only, but later I came to know that he's from mechanical. So that's a difference. If you see, is the CV, the profile of the students who are graduating in today's years, it's kind of a 360-degree profile. They'll be perfect in every domain, like it can be a part of mechanical, it can be electrical, it can be electronics. So they know a bit about everything, which is really great, as that thing opens a wide variety and a wide domain for a people, so that they can explore more options. Like Abhishek can go in electric vehicle, but with mechanical, electrical, and electronics knowledge, so he's having a lot of choices. And lastly, I'll say that because I'm quite focused on electric vehicle, so I might be doing a 3 months of placement program with Autobot India in the future. And due to this COVID, I'll see how the things work out. But I'll just motivate all you guys. Like electric vehicle is quite a booming technology and will be do wonders in the coming years. And I wish, and I'll say to everyone, to be focused and motivate towards what they want to do. Just focus on an intent, and rest everything will be fine. Thank you.
Thank you so much, Ankit. That was really very motivating. Now I invite Abhishek Pramani to start the presentation on converters.
Thank you, Ankit, for all experiences and thoughts that you have gained in last 5 to 7 years
Thank
of
you. Thank
working.
you.
And I'm also very fortunate to have you as my colleague.
Same here.
And
Same
I'm not.
here.
Thank you. So let's start with our webinar now. Today's webinar is on electric vehicle converters. Our objective is to go through the uh, electronic switches, application and types of converters, features of chopper, classification of chopper, control methods, principles of chopper operation, buck converter, boost converter and its type, buck boost converter, and multi-quadrant converter. It's a lot of things today, so don't worry. I'll go into each one of the topics very casually. So coming into the first part, that is the electronic switches. We have a different quadrant of switch. I'll tell you what quadrant means. We generally have a current and voltage off stages. So the positive direction, that is the top direction, I've taken on stage of current, and the bottom one is off stage of current. Same way in x-axis, I've taken the left side as on stage of voltage, and right side as off stage of voltage. So if any switch is working on one quadrant only, so we will call it a single quadrant. That means it will block the negative current as well as the positive voltage, and it will operate on negative voltage and positive current. So the diode works on that same manner. That means if we are putting a positive signal, means positive voltage through the p side, that is a forward bias, then it will work. If it is on reverse bias, it will not work, right? So the same way, one more switching device we have, that is a transistor, that works on a different opposite stage of it. That means current is on and voltage is off. That means in positive bias, it will work with current as on and voltage off. Now we have double quadrant switches also, which works on two quadrants, like we have MOSFET and IGBT, which will work on both the ways of current, but only on the single side voltage of those device. Like if we put off on stage voltage, the device will not work, whatever current might be. But if we put an off stage voltage, then the device will work, whatever current signal we pass. So these are the working concept of IGBT and MOSFET. They will work on both the quadrants. Now there are bidirectional voltage also, like in whatever voltage we pass through the device, it will work. Pass through the switch, it will work. But with off stage current, the device will not work. That means if I have a diode, think that with the IGBT or MOSFET, if I have a diode which can work on the forward bias only, then it will not let pass the reverse bias current, right? So it will work only with the forward bias current, but it will work on both voltage stages. That means with negative voltage as well as with positive voltage. Now we have multi-quadrant switches also. Think that we have two diodes, PN junction diode, and two MOSFETs arranged in such a manner that it can work with any voltage or with any direction of current. So these multi-quadrant switches are mostly used in converters, in electric vehicle converters, which we will discuss, because this is a major concept of regenerative braking, right? Because in regeneration, what you need to do, the motor need to be operated in case of as like generator, so you need to reverse the current as well as voltage sometimes. So multi-quadrant switches come into the existence. Now let's go into classification of DC-DC converters. There are lots of modes in which DC-DC converters work. There is a very varied classification of DC-DC converters nowadays, but we will majorly look into boost converter, buck converter, and buck boost converter. So there are lots of varied examples of each converter, because it's a very vast chapter. It's as well as the device operations are very vast due to the switching technology that have been developed due to the diodes and semiconductors. So now let's move on to the application of DC-DC converters in electric vehicle. Like there are DC drive system, the electric traction sensors, controllers, and then actuators for entertainment as also, and safety equipment also. We have non-isolated and isolated DC-DC converters for all those things. As non-isolated, I mean that they will not have any particular device like optocoupler or something like that, which will have a total isolation of voltage and current. like buck boost converter, as well as buck converter and buck boost converter, they don't have any isolated system. They are totally intact with all voltage and current. If any device gets harmed, the total device will become fault. Then we have isolated system like flyback, push pull, forward half and half bridge, and full bridge. For regeneration, braking, onboard, backup power, battery recharging, all those things, we have isolated bidirectional DC-DC converters like boost full bridge and boost half bridge. And then for fuel cell systems also, we have boost converter with startup system. So all these systems develop according to the power electronics that you generally study in any electronic and electrical course in the initial stages, that nearly in the initial generally in the third semester of your engineering. So these everything deals with the power electronics. Now coming into the feature of choppers. Choppers is a static device that converts fixed DC input voltage to a variable DC output voltage directly. They offer a smooth control, high efficiency, fast response, and regeneration. A chopper can act as a step up or step down DC-DC device as we wish, and as how we make the circuit. It depends on the circuit that we make. Chopper can operate in either continuous or continuous current conduction mode. Choppers can be built with or without electrical isolation, as I've shown you in the types of DC-DC converters. And then they find application in trolley cars, marine hoists, forklift, trucks, and mine haulers as well. Now, coming into elementary principles, we have high speed on off semiconducting switches. These are very high speed, like especially IGBT switches. It connects source to load and disconnects the load from source at high speed. Continuous triggering on and triggering off at rapid switching speed, and by varying on off time of SCR. SCR is silicon controlled rectifier. The average voltage across the load can also be varied. Now there are two types of DC-DC converter, one with the silicon and other with WBG. WBG is wide band gap. Okay, and now with silicon, the efficiency revolves around 92 to 93%, which allows maximum switching frequency up to 30 kilowatts. And with WBG, drastic improvement in power is observed. That is nearly it is nearly approximate to 50 watt per inch cube, as well as the efficiency, while ensuring the better manufacturability at minimal cost. So this is advanced system that is being developed right now in electric vehicle sector. Due to the electric vehicle sector only, this have evolved in near future. Now coming into classification on the basis of output voltage and current, and on the basis of normal output voltage, we have five classes of converters: one quadrant, one quadrant B, then two quadrant C, two quadrant D, and then four quadrant E, class E. And with the output voltage, we have step up, we call it boost chopper. Then we have step down, we call it buck chopper, and there is a buck boost chopper as well. Now coming into the basis of power loss occurred while device on off, we have hard switch converter and soft switch converter, which we call resonant converters as well. In hard switch converter, on the basis of power, which the power loss is high during switching, that is called hard switch converter. That is, generally occurs due to non-zero voltage and current on the power switches. And while talking about soft switch technology, soft switch converters, it is a type of choppers in which the power loss is very low during switching. It generally occurs due to no voltage or zero voltage or current during the switching. How it happens, we will talk later in this webinar. Coming to controlling methods, we have two types of controlling methods of converters. One is frequency or pulse width modulation control. The pulse width T on, I will uh, measure it with, I will write with T on over here. That depicts the on time of the wave, of the output wave. That is varied keeping chopping frequency. The frequency of chopper is is varied by keeping the frequency constant. The t on time is varied by keeping the pulse on frequency constant, and hence the chopping time period t is constant due to the constancy in frequency. Therefore, the output voltage is varied by varying the t on time, that is the on time of the pulse. So here you can see the t on time is varied in both the left side of the pictures. The t on time is varied, and thus the uh, output voltage of the chopper can be varied accordingly, because it depends the time period of any chopper determines of what the voltage will be at the output circuit. Now, coming into variable frequency control, the frequency of the chopper is varied, that is the time period of the pulse, by keeping the t on and t off time, t on time as constant. Okay, so this method also known as frequency modulation. In frequency modulation, to obtain the full output voltage, range of frequency is to be varied over a wide range. Like you can see here, the time period is being reduced by reducing the t off time, but the t on time is being constant, kept constant in both the graphs. Now, the principles of chopper operation. We, a switch is connected in series with DC voltage source at load and load, right? The switch can be IGBT switch, or I have simply shown here the diode, that is one directional switch, a single quadrant. The switch can be a power transistor or SCR or GTO as well. GTO is gate terminal thyristor, turn off thyristor. Then ideal switch will work with zero resistance when it is in on position, and with infinite resistance in off position, and there will be no lagging in switching. There will be instantaneous switching. The switch can be turned on and off with the help of triggering circuit and commutating circuit respectively. It can be turned on and off as desired at very high frequency, because these are high frequency switches, nearly 30 kilohertz, as we have already shown you the in the specifications. During the turn on period, chopper is in on condition. Okay, and the load voltage is equal to the source voltage, because we have considered it as an ideal switch. During the turn off period, the chopper is in off position, and the load current flows through the freewheel diode. Like I'll show you here. When the switch is in off condition, the freewheeling diode will conduct the current. Why freewheeling diode is used over here? Because whenever there is an inductive load, you must be knowing that an energy is stored in the inductor, that is equal to LdI by dt, which will generally cause spark when there is on or off of switch. Okay, so due to that spark, the heating occurs and the switch may get damaged, or it may catch fire as well. So we need to have a freewheeling diode to eliminate that cause. So freewheeling diode will have the extra current, excess of current, due to LDI by dt effect, and will prevent the switch from damage. So as a result, the load terminals are short circuited by freewheeling diode, and thus the load voltage is zero during turn off period. In this manner, a DC voltage, chop DC voltage is produced across the load, right? So whenever there was in that was in on condition for the time period, that voltage is only sent to the load due to the inductor, because L uh, because inductive voltage will only be transferred to the load over here, and not the voltage what we had given during the turn off time, because that turn off period voltage was not communicated to the load. So from T equal to T on plus T off equation, it is clear that the load voltage depends on two factors: the supply voltage as well as the duty cycle of the chopper. That is the for how much time the T on is present, and also the supply voltage that we are giving. So since the supply voltage is constant, the load now is governed only by the duty cycle of the chopper. In other words, the load voltage is dependent on the factors of T off and T on. Right. Now coming to step down chopper, that is the buck converter that we generally call. The output voltage is less than the input voltage, and the thyristor is in the circuit acts as a switch over here. the thyristor you can see over here. This is not a symbol of thyristor, but we can place a thyristor over here, and this is a switch. So when the thyristor is on, the supply voltage appears across the load. When the thyristor is off, the voltage across the load will be zero. Practical arrangement includes an inductor and a diode, which will eliminate the pulsating effect, providing a smooth DC current. So that will act as a filter circuit. Now, with S closed, D is off. The VI is forward bias diode, and current flows through load, inductor, and diode. This arrangement permits the use of simple filter inductance L and to provide a satisfactorily smooth DC load current. With higher switching frequency, smaller inductance is sufficient to get a load of desired output voltage. When switch is closed, the D is off because the current will not flow in the reverse bias, right? So it will remain off, and the input current builds up exponentially due to the inductor, and the VO equals VI over there, because at that time the circuit is completed through voltage source, inductor, and the load. Now with switch off, the diode will get sorted, because now the inductive current will flow through the diode in the forward bias region. The output of the voltage is equal to the input voltage when the switch is on and diode is reverse bias. The diode current is same as the load current during the T off circuit during the turn off time. So T on and IO is same during turn on time. IO and IN. So you can see here that whenever the switch is on, the current flows through the load. Whenever the switch is off, due to the to eliminate the free will to eliminate the LDI by dt effect, we use the freewheeling diode, and that current flows through the diode over here. Now in boost chopper, the output voltage is generally more than the input voltage by several times. Then inductor is used to provide a smooth input current. The SCR acts as a switch, which works in the PWM mode, and with the switch on, that is S, load is connected to the supply. Then the load voltage VL jumps instantaneously to VI, but the current through the inductor increases linearly and stores energy according to its characteristic. When the S is open, the voltage collapses, and the energy stored in the inductor is transferred to C, that is the capacitor over here, and the diode. Okay, the induced voltage across the inductor reverses and adds to the source voltage. Okay, and this increases the output voltage. The current that will flow through S, that is the switch, now flows through L, D, and C to the load. L is the inductor, D is the diode, C is the capacitor. The energy stored in the inductor is released to the load now. So this way, the voltage adds up due to the inductor as well as the source voltage. Then this acts as a boost chopper. The advantage of this is moderate output voltage gain can be obtained, which is less than 4%. Filtering and meeting EMI requirements are simple for this type of converter. Moderate efficiency can be achieved near to 83 to 85% at full load, and the cost is lower, suitable for option for uh, battery electric vehicle and plugged in hybrid electric vehicle powertrains. But the disadvantage is high voltage gain is not possible. That is, it is not possible to get a requirement of more than 4%, and the required large capacitor to reduce the ripples at the output, because it is in parallelly connected. Now, coming to boost with resonant circuit, that is soft switching. We have boost converter losses occur due to the hard switching, but in switching configuration, the switching losses are eliminated by forcing the voltage to get to zero level. And during the turn on or turn off transition time, either the voltage VDS, that is the source voltage, the device voltage, is zero, or the current IDS becomes zero. As a result, the product of voltage and current is zero. So thus the switching losses can be reduced so that the device can be operated at high switching frequency, which has a huge impact over the volume. And heat sink of the converter can also be reduced in this by this way. So the thermal management of converter will be good if we use a soft switching circuit. The soft switching converter configuration consists of two switches. One is the main switch, that is the S1, and another is the auxiliary switch, that is S2. The duty cycle of the main switch is higher than that of the auxiliary switch. That determines the average output of the voltage of the converter. The auxiliary switch Q2 enables the main switch to operate in soft switching mode. Now the advantage of this is it will have a reduced or a reduction in size and weight of the heatsink, and the safety regulations can be met easily because temperature will be in controlled range, and during abnormal conditions such as over voltage or under voltage, the converter will be under protection. Now this converter can only suitably work with less than 5 kilowatt systems. Substantial output voltage gain is not possible in this type of converter as well. Now with full bridge boost converter that I have shown you in the schematic diagram yesterday in controller system, this is the full bridge boost converter. This converter has three functional stages. One is the inverter, this with four switches over here. Then there is a transformer, AC voltage, which converts the high voltage AC to a low voltage AC. And then sorry since it's a boost converter, it will convert a low voltage AC to high voltage AC. Then there is one rectifier which will convert the AC to DC source. Now the duty cycle of the PWM can be increased or decreased promptly so that output voltage is held constant even with the varying input source voltage. So according to the PWM signal, we can vary the voltage. Now, however, the duty cycle needs to be kept above 50% to protect semiconductor switches. Hence, identical control signals are used in two legs, which alternate with period duration. As the HFT is used, as an HFT is used, that is high frequency transistor, a high step up voltage is possible. Uh, Moreover, it provides galvanic isolation because we have one transformer over here that will provide galvanic isolation between the input side and the load side. At 30 kilowatt load, the efficiency of the converter is appropriately 91.5%. Then, although this converter has moderately high efficiency, the effect of HFT leakage inductance is crucial because of high electrical stress in the switching circuit. Thus, a clamping circuit is required to resolve the peak voltage issue in the switching account. A buck boost converter, which is a combination of buck as well as a boost converter, we can use in either way. If the load is replaced with the source, then it will work as a buck converter. If the load as well as if the load is replaced with the source of high voltage, then it will work as a boost converter. So it combines the concept of both step up and step down choppers. The output voltage is either high or low according to the input voltage. The output voltage polarity can also be reversed over here. The switch is either an SCR, GTO, or IGBT. When switch is on, D, that is the diode, is reverse biased and current is zero. The voltage across the inductor is equal to the voltage across the input when the switch is on. The capacitor supplies the energy to the output load. When the switch is in off condition, the current through the inductor increases linearly with time because of its inductive characteristic. Then with the switch off, the source is disconnected over now. Then the current through the inductor does not change instantaneously, and in forward bias the diode, and thus provide a path for the load current. Now the output voltage becomes equal to the inductive voltage. So with switch on, that is when the t is time on during the pulse width modulation, the w will be on, that is equal to vi into I into t on. With switch off, we have power on equal to vi into ii into t off. So this t off will get cut off over here, and t on will be add up to the voltage across the output. Now we have also this is a very important concept over here, that because when a motor needs to be working as a motor and it needs to work as a generator, is very important to get into the concept of converter. Because at different mode of transportation we need a different mode of working in electric vehicle. It's not like an IC engine that it will directly give load, and it will work as a forward moving vehicle only. It, since it doesn't use gears, uh, through the converter itself we can directly control the working of the motor as a motor or generator. So in the first, the top part, I have taken positive torque and current and in y-axis, and coming to x-axis, the positive part is the positive voltage and positive speed, that is RPM. So when you want to move a top hill, you want greater torque as well as greater speed, and the motor is producing torque, that is we call it motoring, and then the external power source supplies the current, right? The battery will be supplying the current. When the motor is need to be braking, at time we need regeneration. So the motor is producing positive torque, and back EMF supplies the current. So, and now coming to the third quadrant, the motor is producing negative torque because you are motoring in the reverse direction, and the external power source supplies the current over here because you need negative torque as well as negative current. Now, coming to the second part, that is 2 written over here. This is what we need. We generally call the regeneration, the second and fourth quadrant. The motor is producing negative torque because it need to brake in a downhill condition, and back EMF will supply the current. So we can see here that the first and third quadrant are generally motoring conditions, and second and fourth quadrant are generally the regenerative conditions. Now, coming into the type of chopper according to the quadrants: single quadrant, double quadrant, and multi quadrant. So, when the this is type A, the first quadrant, that is a single quadrant chopper. So, when the chopper is on, the supply voltage is connected across the load. Okay. When the chopper is off, V load is equal to 0. The load current continues to flow in the same direction through the diode, the freewheeling diode. The average values of output voltage and current are always positive. The class A chopper is a step down chopper in which the power always flows from source to load. It is used to control the speed of DC motor. Over here you can see the with the time duration how the voltage is controlled across the load. So if you take an RMS voltage, it will always be lower than the maximum voltage, right? So that is the concept that PWM uses to control the voltage across the load. Now, coming to the second quadrant chopper, we have load that contains a DC source, that is E over here, like battery. When the chopper is on, battery drives a current through load through inductor, and the chopper in a direction opposite to that shown in the figure. Okay. The duration of on period of the chopper, the inductance stores the energy, and during the chopper, when the chopper is off, the diode deconducts, and the part of energy that is stored in inductor, that is returned to the supply. So over here, uh, while coming to chopper B, we have operation at the second quadrant, in the second quadrant, where current is negative and voltage is positive. That switch is connected over here. While coming to chopper A, we have voltage is positive and current also positive. So we have the first quadrant switch over here, while in chopper in type 2 we have second quadrant switch. The switches that I have already covered, those switches need to be connected. those what I'll say, the framework of switch need to be connected over here. So the same concept is applied over here. The that is the pulse width modulation, and in same way the RMS voltage will also always be less than the peak voltage. So by controlling the peak, the time duration, that is the pulse, or when the pulse time on, we can control the RMS voltage and the load output voltage. Now coming to type C, that is two quadrant chopper. The class C chopper is a combination of class A and class B choppers in parallel. Okay, these are the two types of choppers that we have discussed right now, that is in negative current as well as in positive current, but the voltage need to be positive in both the quadrants. So taking first quadrant and second quadrant and combining it in parallel way, we can make a chopper of two quadrant. So the advantage of this is we can have both way control. Like over here in the graph, you can see that we can either have a negative current and decrease the voltage, as well as we can have a positive current and increase the voltage of the chopper. So what it does when on turning off on turning on the CH1, that is chopper 1, and FD, the freewheeling diode, this one, they operate together as type A chopper, right? These two, CH1 and FD. Now on CH2 as well as D2, these two operate as a type B chopper in the second quadrant. When CH1 is on, the load current is positive. Okay, when CH1 will be shut on, the load current will be positive. Then on turning off the CH2, like this way, then on turning off the CH2, the energy stored in the inductor drives the current through the diode 2. When CH2 will be off, the current will go through diode 2, because that will come in forward bias now. The average output voltage is positive because of the presence of FD diode, the freewheeling diode. The average output current can take both positive as well as negative now, because it can either go in this direction or it can either go in this direction through this diode. The output voltage is equal to V, and the load receives power from the source now. So this was the concept of type C chopper. The choppers CH1 and CH2 should not get turned on at the same time, because in that case there will be short circuit of the diodes and it will burn off. So we need to have a logic over here, logic control, so that both the choppers should not get uh, initiated simultaneously. Now type C chopper can be used both for DC motor control as well as regenerative braking of DC motor, and type C chopper can also be used as a step up or step down chopper. Now type D is also a two quadrant chopper, or type B chopper. The type D is a two quadrant chopper, right? So both CH1 and CH2 are triggered simultaneously. The output voltage V is equal to Vs. That is, uh, when this in this kind of chopper, both are in series. That is, CH1 and D2 and CH2 and D1 are connected in such a way that we need to switch on both. We need to trigger both the switches simultaneously, so that the Vs and Vo will be equal. Now when CH1 and CH2 are off, the load current continues to flow in the same direction through the load D1, the load D1, and D2, due to the energy stored in the inductor. Now the voltage output VO will be negative of the voltage source. The average load voltage is positive if the chopper on time is more than the off time, right? The average output voltage becomes negative if T on is less than T off. So here you can see that if the T on is greater than T off, then it will have a negative output, negative voltage over here, like this part. Now if the T on time is more than T off, then it will have a positive voltage because the positive part will dominate over Vs plus will dominate over here. So if the T on time is greater than 0.5, then the average value of VO and IO are positive and power flow from the source to load. But if the T off time is greater than zero point 0.5, then the average voltage output is negative and current is positive and the power flows from load to source. So this type of chopper can also be used as a regeneration and as well as motor, because it can be used in both the ways by changing the pulse duration, that is T on and T off. Now coming to type D or two quadrant chopper. So forward motoring operation. In forward motoring operation, it is the first quadrant operation, that is I and V are positive. When switches T1 and T2, this is T1 and over here T2, are conducting, both the output current and voltage output are positive, right? Now the circuit path will be Vs T1, Vs T1, L, R, then E, then T2, then Vs again. So that will be the circuit path. The power will flow from the source to load. This is known as rectifying operation. Now in mode 2, we have reverse braking mode operation. It is a fourth quadrant operation in which T1 and T2 will be switched off, and then the path will be like it will be in a reverse mode. That is, inductor it will give energy to the battery, that is L R E D1, then Vs, then D2. This will be the path of operation. Here the output voltage output current is positive, but the output voltage is negative, right? So that is the power flows from load to the source. Thus we can achieve reverse braking operation in this case. Here the motor speed can be controlled by changing the duty cycle of the switches, because as I previously told that by changing the T on and T off time, we can vary the whether it needs to move from load to source, or whether it needs to move from source to load, as well as vary the uh, amplitude of the voltage, that is whether it can be positive voltage or the negative voltage. Now type E chopper, that is a four quadrant chopper. The first quadrant, ch2 ch3 are off, and ch1 and ch4 are operated. The ch2 ch3 are off, ch1 and ch4 are operated now. Okay, so in this case, when ch1 and ch4 are triggered, that is they are switched on, so it will flow have it will have the current will flow in positive direction through ch1 and ch4, and with output v0, that is load voltage, which will be equal to source voltage. This gives a first quadrant operation. With ch1 equal to off, that is positive current freewheeling through ch4 and d2, the ch4 is over here and t2 is over here. So now it will have a first quadrant operation freewheeling. That means all the circuit is off, the load is disconnected from the source, and the ldi by dt current will flow through the diode over here. So both vo and io are controlled in the first quadrant. It acts as a step down chopper now. Now coming to second quadrant operation of a multi quadrant chopper. In this case, ch2 will is operated, and ch1, ch3 and ch4 are kept off. Okay, so with ch2 on, reverse current will flow through inductor, ch2, d4 and e. The inductor will store energy due to on stage of ch2, and vo is greater than vs, resulting is in negative current. So the chopper is in step up mode, and load must contain E. So here this is the four quadrant chopper operation, I have mentioned. One chopper is on the first quadrant is on step up, two choppers on, then it is in step down. One choppers on, CS3 operated, CS3 and CS2 on, CS3 off, CS2, CS and D4 conduct the E in reverse. That is, the output voltage will be reversed. One choppers on and step up, and then CH4 is operated, CH4 and D2 is operated, the L, that is the inductor will store charge, CH4 will be kept off, and D2 and D3 conducts the uh, voltage in reverse direction, but the current over here will be in positive direction. So in this way, all the four modes that we have discussed in motoring and torque control, as well as whether the motor will be used as a motor or current control, can be controlled. Current control can be controlled through this four quadrant chopper. So this is the third quadrant explanation. This is the fourth quadrant that I have now just now explained using two choppers on step down and one chopper on step up. So that's it for today. Converter topology for DC-DC have been covered, and we have also covered the operation of boost converter, buck converter, and buck boost converters. And we have seen the differences, how different modes of controlling the motor as well as controller giving output to it, so that there will be different mode of operation. We can have regeneration as well as reverse motoring, as well as motoring, normal motoring, and throttle using the converter itself. That is a main concept of today's session. Thank you.
So we are done with today's session, and there are no doubts yet.
Okay.
So, so if anyone having any doubt, you can rewatch the session. It is available every time. You can rewatch the session and ask questions in the WhatsApp group. The link is in the description below. So
Okay.
we can end the session right now.
Thank you, everyone.
Thank you everyone for joining us. Thank you, Ankit.
Yeah. Yeah.
Thank you, thank you, thank you.